Welcome everyone to our presentation on the comparative analysis of machine learning and deep learning models using the Wine datasheet. This project explores how different AI models perform in classifying wine types based on their chemical properties. Our study involves a range of machine learning algorithms including decision tree, random forest, and naive Bayes, as well as deep learning approaches like multi-layer and long short-term memories. Today we will walk you through the datasheet, methodology, result and comparison, highlighting the strengths and weaknesses of each model. Our goal was to evaluate and find the most effective algorithms for this classification problem. We also hope to shed light on when machine learning is more usable versus when the deep learning is advantage. Let's begin by introducing the objectives and dataset we walked through. In this slide, we introduce the concept of AI and explain the key differences between machine learning and deep learning. Machine learning algorithms typically rely on structured data and require features extension for performance, while deep learning models automatically learn complex patterns and represent from the data. In this project, our goal is to classify wine types based on their chemical properties. We will use various machine learning and deep learning models and compare their performance using common evaluation metrics such as accuracy, precision, recall, and F1 score. The motivation behind this project is to identify the strengths and weaknesses of these AI models and understand which approach is better suited for this dataset. By doing so, we can provide insight into how to choose the right model for similar classification problems. This slide provides an overview of the dataset we use in this project. The wine dataset, sourced from Kaggle, consists of 178 samples, each with 13 features describing the chemical properties of the wine. The target variable type classified each wine sample into one of three categories: type 0, type 1, or type 2. The features include important attributes like alcohol content, matic acid, magnesium level, and flavonoids, all of which contribute to differentiating the wine types. The dataset has a fairly balanced distribution among the three wine types, but type 1 has the highest representation with 71 samples, while type 2 has the lowest with 48 samples. The dataset structure is straightforward, making it suitable for both machine learning and deep learning algorithms. In this slide, we delve into the dataset statistics. We highlight key features like alcohol, malic acid, and magnesium, which vary significantly across different wines. For example, alcohol content range from 11 to 14.83, while magnesium level range from 70 to 162. These wide range indicate the diversity in the wine samples. The mean value for these features give us an idea for the typical wine composition, with an average alcohol content of 13 and magnesium level of 99.74. We also observe that the dataset's class distribution is somewhat imbalanced, with type 1 having the most samples and type 2 the least. These insights provide a solid foundation for understanding how the features contribute to wine classification, and the models will interpret this data. Before we apply any models, it's important to understand the dataset through exploratory data analysis. EDA helps us identify patterns, outliers, and correlations within the data. For this analysis, we use various visualization, including distribution plots, to observe how each feature is spread, box plot to identify outliers, and scattered plots to examine relation between the features. For instance, we notice a strong positive correlation between the flavonoids and total phenols, indicating that these features might contribute similarity to the target variable. Identifying this pattern is crucial for model development as it helps us decide which features to emphasize or ignore when training the models.
A feature correlation metric is a valuable tool that helps us understand the relation between different features. In this heat map, we can see the strength of correlation between variables. For example, flavonoids and total phenol have a high positive correlation, suggesting that they may provide similar information to the model. Alcohol content and proline also show a moderate positive correlation, indicating this feature might be important predictor of wine type. By identifying this correlation, we can make an informed decision about feature selection, ensure that our model are not overloaded with the redundant information. This analysis also guides us understanding which feature contribute most different between wine types. Feature selection is a critical step in preparing the dataset for model training, especially when working with the algorithm sensitive to feature magnitude, such as deep learning and distance-based method. In this case, we use the standardized scalar to normalize all features, ensure that they have a mean of 0 and standardized deviation of 1. This step is crucial because of wine datasets contain features with varying range. For example, alcohol content range from 11 to 14, while proline level vary from the 278 to 1680. Without scaling, model could give undue importance to feature with a large values, leading to biased result. By standardizing the features, we ensure that all of these contribute equally to the model learning process. In this project, we evaluate 5 different models, 3 from machine learning and 2 from deep learning. The machine learning model include decision tree, random forest, and naive Bayes, which are widely used for the classification task. On the deep learning side, we use a multi-layer perceptron and a long-term term memory. Each of these models has a different strength and the weakness, making them ideal candidates for comparison. Our objective was to assess which model performed best for this specification classification problem. Throughout the evaluation, we paid attention to both their accuracy in making prediction and their computational efficiency. To evaluate the performance of our model, we use 4 key metrics: accuracy, precision, recall, and F1 score. Accuracy tells us the overall percent of correct prediction, but it may not always the best measure, especially for imbalanced dataset. Precision focus on the how many of predicted positive case were actually correct, while recall measure the ability of the model to find all positive instances. F1 score combine both precision and recall, providing an imbalanced matrix for a performance evaluation. In addition, we used a confusion matrix to visually assess how well each model classified the wine type. The combination of metrics provides a comprehensive view of model performance. Decision tree model performed well on the wine dataset, achieving an accuracy of 0.93 with the precision, recall, and F1 score all at 0.93. Decision trees are known for the interpretability. In this case, the model provided clear decision rule for clarifying wine type based on chemical properties. However, one drawback of the decision tree is that they can overfit the training data, especially when dealing with the smaller dataset like ours. Despite this, the confusion matrix show that the decision tree was able to clarifying the most instance correctly. Throughout the few misclassification did occur. Overall, it is a solid model, but there is a room for improvement in terms of the redundancy.
Now we are going to explain the random forest model. Random forest significantly improve upon the decision tree model, achieving an accuracy of 0.96 with equally high precision, recall, and F1 score. This improvement is due to the assembled nature of random forest, which averages the predictions of multiple decision trees to reduce the overfitting. The confusion matrix shows that this model made very few misclassifications, making it one of the top performers in our analysis. Random forest ability to generalize better than single decision tree makes it more reliable model, especially for dataset like this one, where overfitting can be concerned, and it also handle the class imbalance better ensuring accurate predictions across all the wine types. Naive Bayes is a simple yet effective model for classification tasks. Despite its assumption of feature independence, the model performed very well on the wine dataset, achieving an accuracy of 0.96, matching the performance of random forest. Precision, recall, and F1 score were also high at 0.96 across the board. The confusion matrix shows that Navis Bayes made very few misclassifications. This strong performance can be attributed to the relatively simple structures of the dataset, where the feature independence assumption doesn't significantly affect the results. Navis Bayes is efficient, making it an excellent choice for quick, reliable predictions. The MLP achieved perfect scores across the all metrics with an accuracy, precision, recall, and F1 score of 1. While this might seem like an ideal result, it raises a concern about overfitting, especially given that the model made no misclassification. MLP is a deep learning model that can capture complex, nonlinear relationship in the data, which is why it performs so well. However, achieving a perfect result is a rare in real world datasets, and it suggests that the model may have learned the training data too well, possibly at the expense of generalization. Further investigations, such as using a cross validation, would help determine if overfitting is an issue. Long short-term memory (LSTM) is typically used for sequential data, but we apply it to a wine dataset to see how well it could classify the wine types. The LSTM achieved an accuracy of 0.93 with precision, recall, and F1 score all 0.93, matching the performance of the decision tree model. The confusion matrix shows that while the LSTM made a few misclassifications, it performed comparatively to a machine learning models. Given that this dataset is not sequential, LSTM performance is still impressive. However, it requires more training time than the other model, making it less efficient for this particular problem. These slides represent a visual comparison of models based on accuracy, precision, recall, and F1 score. As you can see from the bar chart, the multi-layer prescription MLP achieved the highest performance with perfect scores across all metrics. Random forest and Navis Bayes follow closely, both with strong performance and accuracy of 0.96. LSTM and decision tree perform well, but slightly below the random forest and Navis Bayes. This comparison highlights the strength of assembled learning and deep learning, with MLP outperforming the traditional machine learning model. However, MLP's perfect score suggests possible overfitting, whereas random forests provide a more balanced and reliable approach. In conclusion, our analysis showed that the MLP was the best performing model, achieving perfect accuracy, precision, recall, and F1 score. However, the flawless performance raised concern about overfitting, which could limit its generalization in real-world scenarios. Random forests emerged as a most balanced and reliable model, providing high accuracy without overfitting. Navis Bayes, despite its simplicity, also performed exceptionally well. The deep learning model, while powerful, required more computarization resources and training time. Moving forward, hyperparameter tuning and explorations of additional deep learning architectures like convolutions neural networks (CNN) could further improve model performance. Thank you for your time and attention.